Hi boys and girls, this is lecture 8.3. Today's review topic, implicit differentiation and slope fields. What is implicit differentiation? There are equations in which you are able to solve for y explicitly, therefore able to differentiate explicitly. There are other equations in which you are not able to solve for y explicitly, therefore you must differentiate implicitly. First, we'll take the derivative of each term with respect to x. 4 dx dx minus 6y dy dx plus 7, we'll have to use the product rule for xy, x dy dx plus y dx dx equals 0. The dx dx terms cancel, but the dy dx terms remain. 4 minus 6y dy dx plus 7x dy dx plus 7y equals 0. Collect all of the dy dx terms on one side of the equation, then factor out the dy dx. Negative 6y dy dx plus 7x dy dx. We'll move the other terms to the other side of the equation. That will equal negative 4 minus 7y. Then we'll factor out the dy dx. Negative 6y plus 7x equals negative 4 minus 7y. Solve for dy dx by dividing both sides of the equation by the factor which is next to dy dx. Therefore, dy dx will be negative 4 minus 7y over negative 6y plus 7x. What is a differential equation? A differential equation is implicit differentiation in reverse. Here are some examples of differential equations. dy dx equals x plus 2. dy dx equals 5x over y. dy dx equals the square root of x, y. We solve differential equations by using a technique called separation of variables. This means we separate the dy differential, placing dx with the x terms and dy with the y terms. Let's practice that with these examples. In this first example, I'll multiply dx to the right side of the equation. dy is equal to x plus 2 dx. Now, the dx differential is with the x terms in the equation. In this second example, I'll multiply dx to the right, but I'll also multiply y to the left side of the equation. This results in y dy is equal to 5x dx. Now, the dx differential is with the x terms, the dy differential is with the y terms. In our third example, we'll multiply dx to the right side of the equation, but we'll also divide by y, resulting in dy over y is equal to the square root of x dx. Now, the dx differential is with the x terms, and the dy differential is with the y terms. When the variables are separated and matched with the correct differential, integrate both sides of the equation to get the solution to the differential equation. In this first example, I'll integrate both sides and get y equals 1/2 x squared plus 2x plus c. In the second example, I'll integrate both sides and get 1/2 y squared is equal to 5/2 x squared plus c sub 1. This constant will undergo another transformation, so I'll label it c sub 1 until it reaches its final form. Now I'm going to multiply both sides of the equation by 2. Y squared is equal to 5x squared plus 2 times c sub 1, which is just another constant, c. In the third example, I'm going to integrate both sides and I'll end up with natural log of y is equal to 2/3 x to the 3/2 plus c sub 1. Again, since this constant will undergo another transformation, I'll label it c sub 1 until it reaches its final form. I'll need to exponentiate both sides of this equation to solve for y. This gives me y equals e to the 2/3 x to the 3/2 plus c sub 1. But I can write the right side of this equation as e to the 2/3 x to the 3/2 times e to the c sub 1. But e to the c sub 1 is another constant, and it will become the coefficient of this e to the x term. So y is equal to c e to the 2/3 x to the 3/2 is the solution to that differential equation. Once you've found the general solution, you can use an initial condition to solve for a specific solution. Let's find the particular solution to the given differential equation, given that y of -2 is equal to 1. First, I'll subtract this term to the right side of the equation and write y prime as dy dx. This gives me dy dx equals -y x plus 1. Now I'll multiply dx to the right side, but I'll also divide by y. This results in dy over y equals, and distributing the negative, -x minus 1 dx. Now we can integrate both sides of the equation. This gives me natural log of y is equal to -1/2 x squared minus x plus c sub 1. Again, this constant will change, so I'll label it c sub 1 until it reaches its final form. Exponentiating both sides of the equation to solve for y gives me y equals e to the -1/2 x squared minus x plus c sub 1. But I can write this as y equals e to the -1/2 x squared minus x times e to the c sub 1. This is another constant, so it becomes the coefficient of this term. Y equals c e to the -1/2 x squared minus x. This is the general solution, but now we're going to use the initial condition given to find a particular solution. 1 is equal to c e to the -1/2 -2 quantities squared minus a -2. 1 is equal to c e to the -2 plus 2, which becomes e to the 0, which is 1. So 1 is equal to c. Therefore, our particular solution will be y equals 1, which I don't need to write, e to the -1/2 x squared minus x. Slope fields. A slope field is a way of visually representing the family of solutions of a differential equation. To construct a slope field, draw a short line segment at each point in the coordinate plane, which represents a slope at that point. If our differential equation, dy dx, is equal to x over y, let's find the slope at each of these ordered pairs. 1 over 1 is 1. 0 over 1 is 0. 1 over 2, 1/2. -1 over 1, -1, -1 over -1, +1, and -2 over 0, undefined. Now at each of the ordered pairs, I'll draw a short line segment representing the slope. So at 1, 1, I'll draw a short line segment with a slope of 1. At 0, 1, I'll draw a short line segment with a slope of 0. At 1, 2, a slope of 1/2. At -1, 1, a slope of -1. At -1, -1, a slope of 1. And at -2, 0, an undefined slope, which is a vertical line. From the slope field, you get a picture of what the general solutions to a specific differential equation look like. You can also begin to see patterns. For example, the slope is always 0 when x equals 0, as long as y is not 0. So all along here, we would have 0 slopes. And it's always undefined when y is equal to 0, as long as x is not equal to 0. So that means we'd have undefined slopes all along here. Now let's do a couple of free response questions from previous AP exams. This one is from the 2008 AP exam. And notice it's number 6, so it's on the non-calculator portion of the exam. Letter A states, show that dy dx is equal to negative quantity x plus 1 over 2 quantity y cubed plus 1. So let's differentiate implicitly this equation. I'll rewrite it. X squared plus 2x plus y to the fourth plus 4y is equal to 5. 2x dx dx plus 2 dx dx plus 4y cubed dy dx plus 4 dy dx is equal to 0. That means I'll have dy dx 4y cubed plus 4 is equal to negative 2x minus 2. dy dx is negative 2x minus 2 over 4y cubed plus 4. We can divide all of these terms by 2, and factoring the negative out of the numerator gives me negative x plus 1 over 2y cubed plus 2. Now let's factor out the 2 in the denominator, negative x plus 1 over 2y cubed plus 1. For letter B, we're asked to write an equation for the line tangent to the curve at the point negative 2, 1. Well, to write an equation of a tangent line, we need two things, a point and a slope. We are given the point, but we need to know the slope at that point. So we need dy dx at negative 2, 1. Let's plug that into our slope function. Negative 2 plus 1 over 2 times y cubed, 1 cubed plus 1. In the numerator, negative 2 plus 1 is negative 1, and negative 1 is positive 1. In the denominator, 1 cubed plus 1 is 2. 2 times 2 is 4. So dy dx at negative 2, 1 is 1/4, and that is our slope. Now let's write the equation of the line. Y minus 1 is equal to 1/4 x minus a negative 2 is plus 2. It is fine to leave your equation in point-slope form. Now let's look at letter C. Find the coordinates of the 2 points on the curve where the line tangent to the curve is vertical. The line tangent to the curve will be vertical where the denominator of our slope is 0. So let's set this denominator equal to 0 and discover those y values. 2 times the quantity y cubed plus 1 is equal to 0. Dividing both sides by 2, y cubed plus 1 equals 0. Notice this is sum of cubes, and it factors this way. Y plus 1, y squared minus y plus 1 equals 0. This means that y plus 1 equals 0 yields the y value at which the tangent lines are vertical. Y equals negative 1. Now we're going to need to plug that back into the original function to find the x values that correspond to a y value of negative 1. So we'll have x squared plus 2x plus negative 1 to the 4th power plus 4 times negative 1 is equal to 5. So this is x squared plus 2x. Negative 1 to the 4th is 1 minus 4, negative 3. And when I subtract 5 over, that gives me minus 8 equals 0. Let's factor this quadratic. X plus 4, x minus 2 equals 0, giving me two x values that correspond to a y value of negative 1. Negative 4, negative 1, and 2, negative 1. So at these 2 points, the tangent line to the curve is vertical, and your answer for letter C would be these 2 ordered pairs, negative 4, negative 1, and 2, negative 1. Now let's look at letter D. Is it possible for this curve to have a horizontal tangent at points where it intersects the x-axis? Explain your reasoning. Well, horizontal tangents will occur when the numerator of the slope is 0. That will be when negative x plus 1 is equal to 0, which will be where x plus 1 equals 0, and that will occur at x equals negative 1. But the curve will be crossing the x-axis when y equals 0. So we need to see if it's possible for x to be negative 1 and y to be 0 simultaneously in this equation. So we'll have negative 1 quantity squared plus 2 times negative 1 plus 0 to the fourth plus 4 times 0, and we're going to see if that does equal 5. 1 minus 2 plus 0 equals 5 is not a true statement. Negative 1 does not equal 5. So it's not possible for x to be negative 1 while y is 0. Therefore, it's not possible for the curve to have a horizontal tangent at points where it intersects the x-axis. Here are the scoring guidelines for that question. On letter A, 1 point was given for correct implicit differentiation, another for verification. On letter B, 1 point was given for correct slope and another for the correct equation of the tangent line. On letter C, 1 point was given for identifying y as negative 1, a point was given for substituting negative 1 into the equation of the curve, and another point for the answer, which were the two ordered pairs. For letter D, 1 point was given for recognizing that the equation had to work with x equals negative 1 and y equals 0, and another point was given for your answer with a reason. Our last example is a free response question from the 2005 AP exam. It's also on the No Calculator Allowed portion of the exam. Consider the differential equation dy dx equals negative 2x over y. On the axes provided, sketch a slope field for the given differential equation at the 12 points indicated. In the interest of time, I went ahead and calculated all of those slopes and constructed the slope field. So let's move on to letter B. Let y equal f of x be the particular solution to the differential equation with the initial condition f of 1 equals negative 1. Write an equation for the line tangent to the graph of f at 1, negative 1, and use it to approximate f of 1.1. Well, to write the equation of a tangent line, we need two things, a point and a slope. We're given the point, 1, negative 1. We just need the slope at that point. So we need dy dx at the point 1, negative 1. That's going to be negative 2 times 1 over negative 1, which is 2. Therefore, our slope is 2, our point is 1, negative 1, and our equation of the tangent line, y plus 1 equals 2 times x minus 1. But that was only part of what was asked for in letter B. We need to use the equation of the tangent line to approximate f of 1.1. Y plus 1 is equal to 2 times 1.1 minus 1. Y plus 1 is equal to 2 times 0.1. Y plus 1 then is equal to 0.2, which means that y is equal to negative 0.8. And that is the second answer for letter B. Now let's look at letter C. Find the particular solution y equals f of x to the given differential equation with the initial condition f of 1 equals negative 1. So we'll use separation of variables to solve this differential equation. dy dx is equal to negative 2x over y. I'll multiply by the dx and by the y. Y dy is equal to negative 2x dx. Let's integrate both sides. This gives me 1/2 y squared is equal to negative x squared plus c. Now let's use the initial condition to solve for c. I'll have 1/2 times negative 1 quantity squared is equal to negative 1 squared plus c. This becomes 1/2 is equal to negative 1 plus c, which means c is equal to 3/2. This results in 1/2 y squared is equal to negative x squared plus 3/2. Let's multiply through by 2, and then we'll have y squared is equal to negative 2x squared plus 3. Now you can see that this is an equation of a circle, and because our particular solution goes to the point 1, -1, we're talking about the bottom half of the circle. So our particular solution will be y equals negative square root of negative 2x squared plus 3. Here are the scoring guidelines for that question. Notice on letter A, 2 points were awarded, 1 for the zero slopes and 1 for the non-zero slopes. On letter B, 2 points were awarded as well, 1 for the equation of the tangent line and 1 for the approximation at 1.1. 5 points were awarded on letter C, 1 for separation of variables, 1 for the antiderivative, 1 for the constant of integration, 1 for using the initial condition to solve for c, and 1 for solving for the particular y. Notice that a maximum of 2 out of 5 is given if there's no constant of integration here, and 0 out of 5 if there was no separation of variables. Tip number 3 for the AP Calculus AB exam. Do not let the points at the beginning keep you from getting the points at the end. If you can do Part C without doing A and B, do it. If you need to import an answer from Part A, make a credible attempt at Part A so that you can import the possibly wrong answer and get your Part C points. Common student error number 3. Plus C, omitting the constant of integration, especially in initial value problems. We saw that in the previous free response question. Without the plus C, none of the subsequent points would have been awarded. Plus C, very important. That's it for today's lecture. God bless you, boys and girls.